simulators.
Thank you for the introduction. Today I'm going to be discussing our work in developing an error mitigation method which specifically targets the constraints of analog quantum simulators. In particular, the idea is to try to use these post-processing methods to push the noisy quantum evolutions of these systems as far as we can and to recover higher quality observables under these noisy dynamics. In particular, we've adapted a zero noise extrapolation method to particularly target a type of control error which dominates on certain types of AMO platforms. First, I want to be on the same page about what I mean by analog quantum simulation, which is just to say Hamiltonians where we have some continuous time dynamics, and we're mapping some system that we have onto a model that we want to study kind of either directly or effectively. There's a variety of platforms that you can use kind of as on the system side. And of course, as we've heard in this conference, a variety of models that we might be wanting to study using this regime. The main advantage of analog quantum simulation is that we can access larger system sizes and kind of more direct dynamics of these evolutions instead of kind of discretizing things and doing some digital quantum simulation. The main disadvantages, though, is that you're limited necessarily in the Hamiltonians that you can try to study with these systems. And I want to highlight this third point, which is that there's no yet concept of scalable quantum error correction for analog quantum simulators, which means we're always going to be in a bit of a noisy or NISQY regime when we're trying to get outputs on these devices. This leads us to the kind of natural question of what can we do given a kind of the state-of-the-art noisy analog quantum simulator? How can we try to use post-processing techniques or error mitigation techniques to improve these outputs? This brings us kind of to this idea of error mitigation, which has been especially developed for digital quantum simulation and digital quantum computing. However, analog quantum simulation is in a fundamentally different regime. We don't have this idea of fault tolerance kind of looming on the horizon where we're ultimately trying to work within these error-corrected codes. For noisy quantum simulation, or for analog quantum simulation, we're always going to have a device and try to make the most that we can out of the device that we're given. And I want to propose that error mitigation methods are going to be kind of a fundamental tool in the toolbox of experimentalists in using these systems. In the rest of this talk, I'm going to present kind of the error model that we decided to focus on that is specific. It's general to kind of types of control errors and especially shows up on some analog quantum or AMO type devices. We then develop an error mitigation method and formalize the framework for zero noise extrapolation for mitigating these types of errors and show experimental work with our collaborators at Duke University. As you can consider the timescale of some experiment and some experimental drift over this timescale. Over very long timescales, if you have some parameter mismatch or miscalibration, a very studious graduate student could keep the system very well calibrated by regularly adapting the system. Over very short timescales, we can treat these types of noise as Markovian types of noise, and we don't necessarily think of them as kind of coherent errors. There's kind of an intermediate timescale regime, though, which we call shot-to-shot fluctuations, which is where the drift of your parameter is slow relative to the timescale of a single shot, but fast relative to the timescale it would take to calibrate your system. So you can't necessarily tune the knobs fast enough to cancel these things out. In a Hamiltonian picture, we can think of this as every shot or trajectory of the system is under some unitary dynamics, h, where we have the model we want to study, h naught, and some perturbation of that model, v. The idea here, though, is that we're going to sample the strength of this perturbation from some distribution to model these shot-to-shot fluctuations. As a very concrete example, consider the idea of like single-qubit Rabi flopping. We drive kind of coherent evolutions between the 0 and 1 population state under this X drive. However, if we perturb it with a kind of control error, which is thermally distributed, these different oscillations and trajectories will add up and have different dynamics. Of course, we can't measure a single trajectory of our system, and so when we take kind of expectation values of this system, we get the effective kind of damping noise. I also want to highlight that this model captures a particular type of control error, which is when the error Hamiltonian is not necessarily orthogonal to the dynamics that we want to study, which makes doing something like dynamic decoupling much harder to implement. In experimental systems, this type of noise shows up, especially due to like low frequency noise in the controls. In trapped ion systems, they use the phonon normal modes to mediate interactions on kind of a 1D long ion chain. The radial modes, kind of the into the page and up and down, they use for computation, and you can use that to engineer the Hamiltonian of your system. However, there's these axial side-to-side oscillations, in particular the center of mass kind of long oscillation back and forth, which is particularly susceptible to low-frequency noise and charge fluctuations on the surface of the trap. When you address these ions with a tightly focused beam, it causes them to sample a different effective Rabi frequency over the dynamics of your experiment. And so the effective Rabi frequency depends on the thermal occupation number of this axial center of mass mode. In neutral atom systems, systems that are driven by kind of a global laser beam, you could consider a low frequency or 1 over f noise laser amplitude fluctuations, which cause, when we sample kind of a single shot over a short time scale relative to the kind of shot-to-shot time scale of measurement and things like that and overhead, we get a different effective Rabi frequency every evolution, and we can model this as a white noise distribution. I want to point out that this error model is not necessarily kind of constrained to these types of systems, although these are two kind of physical implementations of where this shows up in experimental systems. For the rest of this talk, I'm going to focus on trapped ion systems in our experimental work with Duke. In particular, in trapped ion systems, this type of error can always be dominant because it grows with the size of the chain length. So you can always kind of push yourself into a regime where this is the limiting type of noise in the system. Now we can kind of turn to how we try to address this type of noise, which is this idea of zero noise extrapolation. The kind of fundamental idea of zero noise extrapolation is relatively straightforward. You assume that you have some expectation value versus noise function. This is kind of hidden to you to begin with. However, we can try to take samples of this function by taking experimental points on our system. You might have some baseline. This is the best calibrated system that you have. And we can try to tune systematically the relative error strength of the system in order to take different samples at different points of this curve. We can then try to fit that to a polynomial and try to extrapolate and recover the expectation value at zero noise. There are two fundamental questions here. One is, when is this measurement versus error strength function well approximated by a low degree polynomial? And also, how do we systematically scale the error of our model? Here we can kind of now try to formalize this idea of zero noise extrapolation under these ideas of kind of distributed noise and the shot-to-shot fluctuations, especially when we're defined in terms of some distribution. You could consider distribution as parameterized by some distribution parameter, which we'll call theta. For a normal distribution, this might be the variance of the distribution, or for a thermal distribution, it's like the temperature of the system. And we have two basic criteria. One is that this theta is a good axis for extrapolation, which corresponds to the moments of the polynomial being polynomials in this parameter. And two, the distribution is sufficiently concentrated, which means the absolute moments for large moments don't scale much faster than factorially. We can then use this to formalize the system, given the system parameters that we have, like the Hamiltonian, the perturbation, this distribution that we have, and what this distribution parameter is, and importantly, a set of estimators at different values of this theta. We can then rigorously bound the zero noise extrapolation error under Richardson extrapolation. We end up with this equation, which is, this particular equation is relatively common to existing zero noise extrapolation methods, where we have the error of the ZNA estimator compared to the ideal expectation value that we want to recover. This error depends on the particular polynomial that we end up fitting to. In Richardson extrapolation, we can construct these polynomials just from the set of thetas that we have. And also the truncation bound, kind of the approximation that we get of approximating this error function as a polynomial, and some sampling error that we get from a finite sampling or projection noise effect. I want to highlight particularly this polynomial truncation method, which is where the dynamics under this shot-to-shot error shows up. Here we have, you can see the polynomial truncation depends on the parameters of the system, like the observable we want to measure, the time of the evolution, the perturbation, the order of the extrapolation, and the moments of this distribution. In a practical setting, we want kind of the first order of this right-hand equation to be relatively close to 1 or less than 1. However, in an ideal world, if you could take a lot of samples and go out to very high polynomials, you could try to suppress this right-hand side by scaling with respect to this factorial on the denominator. Next, I want to turn to our implementation of how to do this on a trapped ion system. In particular, I haven't answered yet how we try to scale this theta distribution parameter in an experimental setting. Turns out that we can turn to the work that the trapped ion experimentalists have done, especially work by Marco Cettina et al. At Duke, which well characterizes this type of noise under single qubit oscillations. So what we'll have to do first is to learn this value of theta for an experimental regime. And we can do this relatively straightforward by measuring single qubit Rabi oscillations and fitting it to the kind of known function for single qubit oscillations, which is this kind of complicated equation here. But importantly, it depends on a parameter theta, which is essentially a witness for the temperature of the ion chain. We can then try to understand how to scale this theta parameter directly, especially in a way that doesn't confound itself with the Hamiltonian we want to study. Again, we can look to the system and leverage the physics of the system, especially where the error actually shows up in the system, which is that it heats up over time due to coupling to kind of external fields. So we'll have this kind of relatively straightforward procedure where we initialize the system and cool down all of these phonon modes, and then we add a delay time. Over this delay time, the baseline temperature heats up, and then we can resume the evolution at a new temperature. Then we can learn this distribution parameter as a function of this wait time and get a linear fit for this, which we'll use as a measure of the error even for like a mini-body system evolution. Of course, we can look at single qubit oscillations here. This is experimental data in these orange and red curves plotted as a function of the experimental time, which is on the microsecond time scale. And I've taken a vertical slice at about 9.5 microseconds to show the kind of inset of how we scale this distribution parameter and do this extrapolation to recover this blue curve. For single qubit dynamics, we expect this to work quite well because the noise is still quite limited. And it shows that we can systematically tune this distribution parameter and recover well the noise-free dynamics. And I also want to point out that we've added more ions to the system than kind of you normally would use, which is we're pushing us into this regime where this is particularly a dominant type of noise. We can also look at 2-qubit exchange oscillations under the same picture. So this is kind of the basic unit of an Ising interaction under a kind of detuned interaction on the trapped ion system. We're flopping between the 0-1 state and the 1-0 state in 2 qubits. And this also allows us to post-select out bit flip errors because we're not interested in studying them for now. There are kind of, here's experimental data that we've collected here. Again, the kind of red curves are the experimental points. And I've taken a time slice at about 1 millisecond. There are 3 distinct regimes in this plot. First is at relatively short time scales, sampling or projection noise kind of dominates the system, and zero noise extrapolation really isn't needed to try to recover a good expectation value. In the intermediate regime, though, we have very good kind of recovery of the noise-free estimator, or the noise-free observable. This is because the noise is relatively well behaved in this regime, and also we have enough samples to distinguish between these different expectation points. However, especially with a thermal distribution, which has moments which scale quite poorly, we expect this method to fail at some point, especially when we can't really trust the dynamics of the system, partly due to this radius convergence concern, and partly due to not taking enough shots to really fully distinguish the expectation values in the kind of longer timescale regime. And with that, we've developed a zero noise extrapolation method, which is generalized to a variety of Hamiltonian models and error models and analog quantum simulation platforms. It's a 3-step process. You start by characterizing the noise quite well, especially at a single qubit level, which is sufficient to understand the dynamics of a mini-body evolution. We then have to find a way to rescale this error. We looked at this for trapped ion systems, and in the archive paper, we've also looked at this for neutral atom systems. And I didn't have time in this presentation to go into the numerical method for looking at mini-body quantum scars and these kind of long time oscillations, which are particularly affected by this type of shot-to-shot fluctuation noise. And then finally, we've rigorously characterized how this performs under this type of shot-to-shot fluctuation and characterized this idea of mitigable distributions, which especially includes thermal distributions and Gaussian distributions, and is a relatively loose set of criteria. And then I'll end by thanking my collaborators on this project at University of Maryland, Duke, Cornell, and IBM Quantum, especially Alexander Schukert, who's here at the conference and was the supervisor on this project, and Di Luo, who's the experimentalist working at Duke and produced the experimental data in this system. And thank you.
Thank you very much, Thomas. We have plenty of time for questions.
Thanks for the talk. So I have a question about robustness of your protocol in the real experiments. Because in your theoretical setup, you said you assume there's a random error with some distribution, and you're able to,